All right, let's talk about group actions. So, let G be a group. And we're going to let X be a set. Just any set. It doesn't have to have anything to do with G. It's just a set all by itself. So we are going to say that that G X on X, or we write G then an arrow thingy X. I don't know if this is standard notation. My professor uses it. I don't know if it's really widespread, but I really like this. It condenses things. I don't have to write the words X on. That's just less stuff for me to do. But anyways, so Gx on X, if there is a map, and this map is going to go from G cross X to X, such that EX equals X for all X in X. Okay, now one thing to note here is I'm not even going to write down, like technically there's a function here. There's a function that takes in an element of G and an element of X and gives you an element of X. I'm not even writing down the function. I'm completely suppressing the notation. So when I say EX equals X, what that really means is there is some function here, like say F, and this function F goes from G cross X to X. And then if you take F and evaluate it at E comma X, then you get X. So there's a lot going on in this definition that isn't written out here. And so if you're learning this for the first time, it might be useful to actually go ahead and give this function a name and write these rules out in terms of these names. But it very quickly becomes really tedious to write out that function name every single time. Kind of like if you remember how when we first introduced groups, we actually gave the group composition law a letter P. And it was like P of G1 comma G2. That was our composition law. That got really tedious really quickly. So to avoid that, we're just going to leave it like this. So this is the first thing. We need, if you apply e to x, that's x for all x and x. And there's only two things you need, and this is one of them. And the other one is G1 of G2 of x equals G1 G2 of x for all x and x, and for all G1 and G2 and G. Now, just like before I had this spiel on this product here, you have to make sure you understand where where all the products here are happening. Here, so this is G2x in this parentheses here. So let's just look at where these elements are, and that should tell us what type of product this is. So we have an element of G times an element of X. Well, then that has to be our group action. But then, so this whole thing is going to give us an element of X. And then we have a element G1 of G acting on an element of X. And so that product is also the group action. So both products on the left side here are the group action. And then here, if we look inside the parentheses, this is G1 times G2. This is just the product in G. So this is just the group law of composition. So this itself has nothing to do with the group action. However, once you consider G1, G2 as a single element of G, then that element of G acts on an element of X. And so this product here is the group action. So we have group action, group composition law, group action. That's where these products are taking place. So we can also define, also, or rather alternatively might be a better word. So if we didn't want to define it as a map from G cross X to X, we can define for all G and G a map, we'll call it tau G from X to X, such that tau of E is just the identity function on X. And let's see, what I have written down here is tau G of tau G inverse equals tau E equals the identity on X. I.e. tau of G is bijective. So instead of defining group actions as a function that takes an element of G and a function from G cross X to X, you can think of it as a function from G to functions from X to X. So it's just whatever comes more naturally to you. I like the first way, but this way is just as good. I'm trying to see, is it immediately obvious that these two are exactly the same? Because if you look at that second statement here, it's not like if you were to translate this one into this language, it should say like tau G2 of tau G1 equals tau G2 G1 or something like that. And I'm sure you could go ahead and prove that those are equivalent. I didn't take the time to do that. So anyway, so what do we end up with? So tau is a map from G to aught X is given by G gets mapped to tau G, and tau is it's a homomorphism. So it's in hom from G to aught X. Now, of course, let's see here. So does this even make sense to say that tau is in hom G aught X? G is certainly a group. Automorphisms on X. Now, X is a set, so there is no composition law, or there is no law, composition law per se on X, let alone one that makes it into a group. But the automorphisms still gives you a group, because you consider here the automorphisms of a set X turns out to be just the bijective maps from that set onto itself, and the identity element is the identity map, which sends every element of X to X, and the law of composition is composition of functions. And I don't think we went into a whole bunch of detail on why that makes sense, but you can sort of iron out the details for yourself if this is unfamiliar to you. Or I guess this isn't really that necessary. You can always just focus on the previous definition. All right, so with that done, we have some definitions that are related to group actions, and that describe certain group actions. So the action of G on X is faithful if tau is injective. So this is stated, it's most easily stated in terms of this tau here. But you can also think of it as it's faithful if you take any two elements of G, they're not going to give you the same law of composition on X. So if you take G1 and G2, then you're going to be able to find some X such that G1 of X, G1 sends X to one thing and G2 sends X to another thing. If it so happens that you have two elements of G which are not equal elements of G, but such that they send every element of X to the same thing, then it's not faithful. So it is free, and I don't like writing words on the left side that are part of the definition, because then I have to underline them, and then it looks like it's its own like definition or proposition or something. So I'm just going to write it's free if for every single x in X, Gx equals X implies G equals E. So here for every single X, the only way that an element of G can fix X is if G is the identity. So basically how you could think of this is that if you're looking at an element of G that isn't the identity, then it's going to move everything in X around. It's going to take everything in X and move it to somewhere new. So that's free. It's transitive if for all x and y in X, there is some G which will take X to Y. So let's look at some examples. Consider Sn acting on the indices from 1 to n. So what is this action? This action is you take an element of Sn. An element of Sn is going to be a bijective map from 1 through n onto 1 through n. So this group action is you're just going to take the indices from 1 to n and just shuffle them around the same way that, shuffle them in the way that this element of Sn tells you to shuffle. And you can go ahead and prove that it's a group action. I'm not going to do that. But, it doesn't take too much time, because if you consider the identity, that's not going to move anything around. So identity acting on 1 through n is just 1 through n. Wait a minute. So Sn doesn't act on, so when Sn acts on this, you take an element of Sn and you take one of the indices from 1 through n, and you send that index to wherever that element of Sn tells you to send that index. So if you take the identity element, if you take any index from 1 to n, the identity element is going to tell you, okay, take that index and send it to itself. And so that holds for all x, and so we have the first thing. And then the second thing is sort of obvious, I think, based on how composition laws work, compositions of functions. Because yeah, the group action in Sn is compositions of functions. And so if you take an element take an index and say, oh, okay, so first do G2 to it and then do G1 to it. That's the same thing as if you were to like take the composition map G1 times G2 and then send the index through that. I think you just write down a whole bunch of notation and it'd be really clear. But anyways, so this is a group action. Let's see here, is it faithful? Is tau injective? So suppose we take two different elements of Sn. Well, if they're different, then there's going to be some index such that it takes that, such that the two permutations will take that index to different new indices. And so if you've got two different permutations, it's going to yield, it's not going to do the same thing to every single index. And so that means that it's faithful. Let's see here. How about free? Right. So if n equals 1, then S1 is just, there's only one map there. And so this holds trivially, so it's always true. What if n is greater than 1? Then, let's see here, consider the map. You know, I have written down here that that this action is not free if n is greater than 1. I'm not so sure about that anymore, because if you consider S2 has two elements. So you have the element which is just the identity map, then you have the element which sends 1 to 2 and 2 to 1. And those are the only two ways you can permute the indices 1 and 2. So if you take an element of x and suppose that our permutation sends that element to itself. Well, there's only two elements of S2. There's the identity, and then there's the one that flips them. And so if it doesn't flip them, or if it keeps the index, then it doesn't flip them. And so it must be the identity. And so unless I'm making some dumb mistake, which is entirely possible, and please inform me somehow if that is the case. But I think I must have written something down wrong here or something. But yeah, when n equals 2, I think this is still free. But what if n is greater than 2? If n is greater than 2, consider the permutation that sends 1 to 2, 2 to 1, and then just keeps 3 in place. Then this permutation will not move the index 3. However, it's also not the identity element of our group. And so there is an x in x, i.e. the index 3 in 1 through n, where n is greater than or equal to 3. And the permutation 1, 2 acting on 3 is 3, but the permutation 1, 2 is not the identity. And so I think it's free if and only if And then we have tree if and only if n is greater than or equal to 3. And what's the last thing? The last thing we have to do is transitivity. Is it transitive? Given any index, say I, if you want to get to j, if you have an index I and you want to get to the index j, consider the permutation that sends I to j and j to I. That'll do it. So it's transitive. All right, so that takes care of that example, and we'll go on and discuss more things about group action.